What if I told you that scientists can't explain why you're conscious right now? Not, we're still working on it. I mean, they have absolutely no idea. Zero. And that's just item number 1 on a list so mind-bending. It'll make you question everything you thought you knew about reality. Right now, in this moment, you're experiencing something. You're seeing colors, hearing sounds, feeling sensations. But here's what will blow your mind. Science cannot explain why any of that feels like anything at all. We can map every neuron in your brain, trace every electrical signal, measure every chemical release, but nowhere in those processes does science find an explanation for why there's a you experiencing it. This is called the hard problem of consciousness, and after centuries of inquiry, we're no closer to solving it than when we started. But consciousness is just the beginning. Right now, 95% of the universe is made of stuff we've never detected, never measured, and can't explain. Quantum particles are communicating faster than light in ways that violate everything we know about space and time. And your own body contains mysteries that would make ancient alchemists feel vindicated. We still can't fully explain how anesthesia works, why we sleep, or what causes the placebo effect to sometimes cure real diseases. Today, I'm taking you on a 3.5-hour journey through 100 things that science, despite all our technology, all our genius, all our certainty, simply cannot explain. And by the end, you're going to see reality very differently. Before we dive in, hit that like button and subscribe, because what you're about to learn isn't taught in schools. And I'm curious, where are you watching from? And what time is it there? Drop your country and the time in the comments. I love seeing how this content reaches people across the planet at all hours. Let's start with the mysteries hiding inside your own head. Item 1. The hard problem of consciousness. Think of it like this. Imagine we built a perfect robot that acts exactly like a human. It talks, laughs, says ouch when you pinch it. But is anyone home? Does it actually feel anything? Philosopher David Chalmers coined the term hard problem of consciousness in 1995 to distinguish this question from the easy problems, like figuring out how the brain processes information or responds to stimuli. Those are just engineering challenges. The hard problem is, why is there subjective experience at all? Neuroscientist Christoph Koch has spent decades trying to find the neural correlates of consciousness, the brain activity that corresponds to conscious experience. He's mapped incredible detail about what happens in the brain when we're conscious. But he admits, we still don't know why those processes feel like anything. It's the difference between describing the chemistry of fire and explaining why fire is hot to touch. Science can do the first, but struggles with the second. Item 2. Why anesthesia works. You'd think we'd understand anesthesia, right? We use it millions of times per year. But here's the shocking truth. We don't know how it makes you unconscious. Dr. Stuart Hameroff, an anesthesiologist at the University of Arizona, has pointed out that different anesthetic drugs have wildly different chemical structures. Some are simple gases, others are complex molecules, yet they all produce the same effect: unconsciousness. It's like discovering that eating an apple, drinking water, and listening to Mozart all make you fall asleep through completely different mechanisms. That doesn't make sense. The best theories suggest anesthetics disrupt quantum processes in the brain's microtubules, but we're still not sure. Think of it like knowing that flipping a light switch turns off the lights, but having no idea how electricity works. Item 3. The placebo effect. Here's where it gets truly bizarre. In clinical trials, people given sugar pills often get better, even when they know they're taking a placebo. Researcher Ted Kapchok at Harvard demonstrated in 2010 that patients with irritable bowel syndrome improved significantly, even when they were told explicitly, "These pills contain no active medicine." How can your mind heal your body when you know there's no medicine involved? The placebo effect sometimes produces measurable physical changes: reduced inflammation, actual tissue healing, pain relief, comparable to morphine. We can see it happening, but we can't explain the mechanism. Your belief shouldn't be able to alter your biochemistry, yet somehow it does. Item 4. Why we sleep. We spend a third of our lives unconscious, vulnerable to predators, and science still can't tell you why. Sure, we know sleep deprivation is harmful, but that doesn't explain why we need to be completely unconscious for 8 hours. Many animals don't sleep the way we do. Dolphins sleep with half their brain at a time. Some birds can fly while sleeping. Giraffes sleep only 30 minutes a day. Dr. Alan Reksha-Fen, who pioneered modern sleep research in the 1960s, famously said, "If sleep doesn't serve an absolutely vital function, it is the biggest mistake evolution ever made." But after decades of research, we still don't know what that vital function is. We have theories: memory consolidation, toxin removal, cellular repair, but none fully explain why we need to lose consciousness completely. Couldn't evolution have designed a system where we rest while remaining aware? Item 5. Left-handedness. About 10% of humans are left-handed, and we have no idea why. Think about how strange that is. This trait has persisted across all human cultures throughout history, despite left-handed people facing disadvantages in a right-handed world. If it were purely genetic, the trait should have evolved out. If it were purely environmental, the percentage would vary more between cultures. But it's always around 10%. Geneticist Silvia Paracchini has studied the genetics of handedness for years and found over 40 genes associated with it, but they only account for about 25% of handedness cases. Something else is going on, and we don't know what. Item 6. Why we have fingerprints. Your fingerprints are unique. You probably know that. But do you know why you have them at all? The common assumption is that they help with grip, but research shows they actually make gripping smooth surfaces harder, not easier. In 2009, researchers at the University of Manchester discovered that fingerprints reduce our ability to grip by about 30%. Some scientists think they help us sense texture through vibration, turning our fingertips into sensory organs. Others think they might help channel water away from our fingers. But nobody knows for sure. We're so uncertain that we can't even agree on whether they're functional or just a random byproduct of how skin forms. Item 7. Why we yawn. You just yawned reading that, didn't you? Or felt the urge to. That's called contagious yawning, and we don't understand that either. The traditional explanation was that yawning increases oxygen to the brain, but studies have proven that's false. People in oxygen-rich environments yawn just as much as people in oxygen-poor ones. The current best guess? Yawning might cool the brain. Or it might be a social signal. Or it might synchronize group behavior. Dr. Robert Praveen, who studied yawning for decades, concluded, yawning may have the dubious distinction of being the least understood common human behavior. Item 8. The runner's high. When you exercise intensely, your brain floods with endorphins, creating euphoria. We've known this since the 1980s. But here's the mystery. Why? Why would physical stress trigger pleasure? The standard evolutionary explanation is that it encouraged our ancestors to keep moving. But that doesn't make sense. Pain should be enough to motivate survival. Why add pleasure? Some researchers now think the runner's high might be an accident, a quirk of how our pain management systems evolved. Your body releases endorphins to manage the pain of running, and the euphoria is just a side effect. But if that's true, it's a remarkably consistent accident that happens across all humans. Item 9. Why onions make you cry. You'd think something this common would be fully explained, right? When you cut an onion, it releases a chemical called syn-propanethiolous oxide, which irritates your eyes. Your eyes water to flush it out. Simple. But here's the puzzle. Why did onions evolve this defense mechanism? It doesn't stop you from eating them. You just tear up a bit and continue cooking. Unlike truly toxic plants, which taste terrible or make you sick, onions just slightly annoy you. From an evolutionary perspective, this is a useless defense. Yet it's so specific and complex that it must have evolved for a reason. We just don't know what that reason is. Item 10. Déjà vu. You walk into a room, and suddenly you're convinced you've experienced this exact moment before. About 70% of people have experienced déjà vu, yet we can't explain it. Neuroscientist Akira O'Connor has done fMRI studies showing that déjà vu activates the parts of the brain responsible for memory conflict detection. Your brain knows. This is new, but something is triggering a false memory signal. But why? Some theories suggest it's a glitch when your brain processes an experience through multiple pathways at slightly different speeds. Think of it like your brain receiving the same video frame twice and interpreting it as a memory. But we're just guessing. Item 11. Why humans are the only animals that cry emotional tears. Every mammal can produce tears to lubricate their eyes, but only humans cry when sad, happy, or moved. Why? Biochemist William Frey studied tears in the 1980s and found that emotional tears have a different chemical composition than reflex tears, like when you cut an onion. Emotional tears contain more protein and hormones. His theory? Crying evolved to remove stress hormones from the body. But that doesn't explain why we'd advertise our emotional state so visibly. Other theories suggest crying evolved as a social bonding mechanism or as a non-threatening distress signal. But none of these fully explain why only humans do it. Now here's where things get really strange. We've been talking about mysteries in human biology and psychology, things happening inside your body that science can't explain. But what about the world around you? Get ready, because the next set of mysteries are going to shake your understanding of reality itself. Item 12. Why ice is slippery. This seems like the dumbest thing on the list, right? Ice is slippery because it's smooth. Done. Except, no. For over 150 years, scientists have argued about why ice is slippery, and we still don't have a consensus. The traditional explanation was that pressure from your weight melts a thin layer of ice, creating water that acts as a lubricant. But research has shown that ice is slippery, even at temperatures far too cold for pressure to cause melting. And it's slippery, even without pressure. The current leading theory involves quantum mechanics. The molecules on ice's surface exist in a semi-liquid state, even when frozen, creating a self-lubricating layer that's neither solid ice nor liquid water. But physicist Robert Rosenberg reviewed the literature in 2005 and concluded we still don't fully understand it. You've been walking on ice your whole life, and science can't fully explain why you slip. Okay, let's pause for a second. We're 12 mysteries in, and already we've seen that science can't explain consciousness, sleep, yawns, tears, or why ice is slippery. If you're still watching, you're starting to realize how much we don't know. And trust me, we're just getting warmed up. If you're enjoying this, hit that subscribe button. We're about to go deeper into mysteries that'll make these first ones seem simple. Item 13. Dark matter. Ready for this? 27% of the universe is made of something we've never detected, never touched, never seen. We only know it exists because galaxies spin in ways they shouldn't if visible matter was all that existed. In the 1930s, astronomer Fritz Zwicky noticed that galaxies in the Coma cluster were moving so fast they should have torn apart. He calculated there must be dark matter, invisible mass, holding them together. For decades, scientists thought he was wrong. Then in the 1970s, Vera Rubin measured the rotation curves of spiral galaxies and confirmed it. There's not enough visible matter to explain how galaxies behave. Here's what will blow your mind. We've built billion-dollar detectors buried deep underground to catch dark matter particles. We've been searching for 50 years. We've found nothing. Not a single particle. Either dark matter is made of something so exotic it passes through our detectors, like we're not even there, or our understanding of gravity is completely wrong. Think of it like this. Imagine you're watching a puppet show, but you can only see the puppets, not the strings or the puppeteers. You know something must be controlling the puppets, but you can't see or measure it. That's our situation with dark matter. Item 14, dark energy. If dark matter wasn't weird enough, 68% of the universe is made of something even stranger, dark energy. In 1998, two teams of astronomers, Saul Perlmutter's team and Brian Schmidt's team, made a discovery that won them the Nobel Prize and broke physics. They were measuring distant supernovae to calculate the universe's expansion rate, expecting to find that gravity was slowly slowing down the expansion. Instead, they found the opposite. The universe's expansion is accelerating. Something is pushing galaxies apart, faster and faster. We call it dark energy, but that's just a name for our ignorance. We don't know what it is, how it works, or why it exists. Here's the truly disturbing part. If dark energy continues accelerating expansion, eventually galaxies will move apart so fast that beings in one galaxy won't be able to see any others. The night sky will be completely black except for their own stars. Future civilizations will look at the universe and conclude they're alone, with no way to know that billions of other galaxies existed but moved beyond the observable horizon. Item 15. Why the universe exists at all. Let's get philosophical for a moment. In the Big Bang, equal amounts of matter and antimatter should have been created. When matter meets antimatter, they annihilate each other in a flash of energy. So the universe should have immediately destroyed itself, leaving nothing but photons flying through empty space. But we exist. Somehow, there was slightly more matter than antimatter, about one extra matter particle for every billion matter-antimatter pairs. Those survivors became everything. Stars, planets, you. Physicist Andrei Sakharov proposed conditions that could cause this asymmetry in 1967. But we still can't explain why those conditions existed, or why the imbalance was exactly the amount needed for galaxies to form. Think of it like flipping a billion coins and having them all come up heads except one tails. Possible? Technically? Likely? No. Yet here we are. Item 16. The universe's fine-tuning problem. The universe operates on physical constants, the strength of gravity, the mass of electrons, the speed of light. If any of these constants were even slightly different, the universe couldn't support life. Change the strength of the strong nuclear force by 2%, and atoms can't form. Change the cosmological constant by 1 part in 10,120, and the universe either collapses immediately or expands too fast for matter to clump together. Physicist Martin Rees identified 6 numbers that seem fine-tuned for life. The odds of all 6 being in the life-permitting range by chance? Astronomically small. This is called the fine-tuning problem, and scientists are genuinely baffled. There are 3 main responses. 1. We're incredibly lucky. 2. God or some intelligence designed it this way. 3. There are infinite universes with different constants, and we obviously exist in one that permits life, a theory called the multiverse. But we have no way to test option 3, which means it might not even be science. It might just be philosophy dressed in scientific language. Item 17. The measurement problem in quantum mechanics. This is where reality breaks down completely. In quantum mechanics, particles exist in superposition. They're in all possible states simultaneously until you measure them. Schrodinger's cat is both alive and dead until you open the box. But here's the problem. What counts as a measurement? Does it require a conscious observer? Does the universe know when it's being measured? Physicist Eugene Wigner seriously proposed in the 1960s that consciousness might collapse quantum wave functions. Others think that's absurd. The universe existed before conscious beings, so consciousness can't be required. The Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg in the 1920s, essentially says, Don't ask what's happening before measurement. Only the measurement results matter. But that's not an explanation. That's giving up on explanation and focusing only on prediction. Physicist John Bell proved in 1964 that quantum mechanics can't be explained by hidden variables. There's no deeper reality determining particle behavior before measurement. The weirdness is fundamental. Reality literally doesn't exist in a definite state until observed. Item 18. Quantum entanglement. Einstein called it spooky action at a distance and refused to believe it was real. But it is. When two particles become entangled, measuring one instantly affects the other, regardless of the distance between them. Change one particle's spin, and the other particle's spin changes simultaneously, even if it's on the other side of the galaxy. In 1982, physicist Alan Aspect performed experiments confirming this really happens. But how? Information can't travel faster than light. That's a fundamental law of physics. Yet somehow, entangled particles are coordinating their behavior instantaneously across vast distances. Some physicists think space-time itself is an illusion, and particles are actually adjacent in some higher dimension. Others think time might not be fundamental. The future might already exist, making the instant communication not communication at all, but rather two ends of a pre-existing connection. We use quantum entanglement for quantum computing and quantum cryptography, but we don't understand how it works. Item 19. The double-slit experiment. This is the experiment that broke reality. You shoot particles, photons, or electrons through two slits, and they create an interference pattern on the detector screen. Bands of light and dark. This proves the particles traveled as waves, going through both slits simultaneously and interfering with themselves. But here's where it gets insane. If you place a detector to see which slit each particle goes through, the interference pattern disappears. The particles start behaving like particles instead of waves. The mere act of observation changes the outcome. Physicist Richard Feynman said, "I think I can safely say that nobody understands quantum mechanics." That was in 1965, and it's still true. We can calculate the probabilities with perfect accuracy, but we can't explain what's actually happening. Does the particle know it's being watched? Does observation create reality? The math works, but the implications are philosophically nightmarish. Item 20. The arrow of time. Why does time only move forward? The laws of physics are time-symmetric. They work just as well running backward as forward. If you filmed particles interacting and played it backward, the physics would still make sense. Yet we remember the past, not the future. Eggs break, but don't unbreak. People age, but don't unage. The standard explanation involves entropy. The second law of thermodynamics says disorder increases over time. But that just pushes the question back. Why was the early universe in such a low entropy state? Why did the Big Bang start ordered and neat rather than chaotic? Physicist Sean Carroll calls this the past hypothesis. We have to assume the universe started in an unlikely low entropy state, and we don't know why. Some physicists think time might not be fundamental at all. Theoretical physicist Julian Barber has argued that time is an illusion created by entropy, that all moments exist simultaneously in timeless physics, and we perceive time flowing because of how our memories are structured. Item 21. Quantum tunneling particles can pass through barriers they shouldn't be able to pass through. It's like throwing a tennis ball at a wall and occasionally having it appear on the other side without breaking the wall. This is quantum tunneling, and it happens all the time. It's essential for nuclear fusion in the sun. Protons shouldn't have enough energy to overcome their electromagnetic repulsion, but quantum tunneling lets them merge anyway. Without quantum tunneling, the sun wouldn't shine and we wouldn't exist. But here's the mystery. When a particle tunnels through a barrier, how long does it take? Does it travel through the barrier, or does it disappear from one side and appear on the other instantly? In 2019, researchers measured the tunneling time and found it was 0. The particle doesn't seem to spend any time inside the barrier. It's here, then it's there, with no journey in between. Think about that. The particle doesn't go around or through the obstacle. It just ceases to exist in one location and begins existing in another. Are you starting to feel like reality is far stranger than you imagined? We're 21 mysteries in, and we're discovering that the universe operates on rules that violate common sense at every level. But hold on. We're about to enter a section that questions whether space and time are even real. Item 22. What is space? Is space a thing, or is it nothing? Aristotle thought space was defined by objects. Where there's no object, there's no space. Newton thought space was an absolute container that exists independently of matter. Einstein showed that space is flexible and curved by mass. But modern quantum physics suggests something even stranger. Space might not be fundamental. Physicist Brian Swingle and others are developing theories where space emerges from quantum entanglement. It's not a real thing, but rather a useful illusion arising from more fundamental quantum information. If they're right, asking, what is space, is like asking, what is up? In a video game, the screen shows up, but it's just pixels. There's no actual up in the computer's memory, just data that creates the appearance of space when rendered. Item 23. What happened before the Big Bang? The Big Bang wasn't an explosion in space. It was the beginning of space itself. So asking what happened before the Big Bang is like asking what's north of the North Pole. The question might not make sense. But some cosmologists think the Big Bang wasn't the beginning. Roger Penrose has proposed conformal cyclic cosmology, the idea that our universe is just one in an infinite series of universes, each beginning with a Big Bang and ending when all matter decays into radiation. That ending state somehow becomes the initial conditions for the next universe's Big Bang. Other theories suggest our universe is a bubble in an eternally inflating multiverse, or that it emerged from a quantum fluctuation in a previous universe's vacuum. We might never know, because any information from before the Big Bang would have been destroyed in the Big Bang itself. Item 24. Why is there something rather than nothing? This is the ultimate question. Why does anything exist at all? Philosopher Gottfried Leibniz asked this in the 1600s, and we're no closer to an answer. Some physicists, like Lawrence Krauss, argue that nothing is unstable and quantum fluctuations inevitably create something. But that just pushes the question back. Why do quantum fields exist? Why are there laws of physics that govern fluctuations? Calling quantum vacuum nothing is cheating. True nothing would have no laws, no fields, no potential for anything. Other thinkers argue the question might be meaningless. Maybe existence is just a brute fact with no further explanation. But that feels unsatisfying. The human mind demands reasons, yet the deepest question of all might have no reason. Item 25. The information paradox. When something falls into a black hole, what happens to the information about it? If a book falls into a black hole, is the information in that book destroyed? According to quantum mechanics, information can't be destroyed. It's a fundamental principle. But according to general relativity, anything that crosses a black hole's event horizon is gone forever, destroyed at the singularity. These two pillars of modern physics directly contradict each other. Stephen Hawking worked on this problem for decades. In the 1970s, he showed that black holes emit radiation, now called Hawking radiation, and eventually evaporate. But his equations showed the radiation was random, containing no information about what fell in. Information was destroyed. This created a crisis in physics. In 2004, Hawking conceded he was wrong, and that information must somehow be preserved, but we still don't know how. Some theories suggest information is encoded on the black hole's event horizon in a holographic pattern. Others suggest information leaks out slowly through Hawking radiation in subtle correlations we haven't detected yet. Item 26. the singularity at the center of black holes. General relativity predicts that at the center of every black hole is a singularity, a point of infinite density where space and time break down. But infinite is math's way of saying, our equations stop working here. Physicist Kip Thorne has said, the singularity is where the laws of physics break down, and we can't predict what will happen. Most physicists believe singularities aren't real. They're a sign that general relativity is incomplete and needs to be replaced by a theory of quantum gravity. But we don't have that theory yet. String theory and loop quantum gravity are candidates, but neither has been proven. So we're in an awkward position. We know black holes exist. We photograph them. We know they have centers, but we literally cannot describe what those centers are like. It's like having a map of your house with one room labeled, "Here be dragons. Map invalid in this region." Item 27. Hawking radiation. Stephen Hawking's most famous discovery might be wrong. He calculated that black holes emit radiation due to quantum effects near the event horizon. And over vast timescales, this radiation causes black holes to evaporate completely. But we've never detected Hawking radiation. For stellar mass black holes, the radiation is so faint, it's drowned out by background cosmic radiation. We'd need to observe a microscopic black hole to detect it, and we've never found one. Some physicists wonder if Hawking radiation exists at all. Without experimental confirmation, it remains a theoretical prediction. If it doesn't exist, our understanding of how quantum mechanics and gravity interact is deeply flawed. Item 28. Quantum gravity. We have two extraordinarily successful theories. General relativity, which explains gravity and the large-scale universe, and quantum mechanics, which explains subatomic particles. The problem? They're incompatible. General relativity treats space and time as smooth and continuous. Quantum mechanics requires everything to be quantized, broken into discrete chunks. When you try to merge them, you get nonsensical infinite values in your equations. For almost a century, physicists have tried to develop a theory of quantum gravity. String theory proposes that particles are tiny vibrating strings in 10 or 11 dimensions. Loop quantum gravity proposes that space itself is made of tiny loops. Other theories suggest gravity isn't even a force, but an emergent property of quantum entanglement. But here's the kicker. We might never be able to test these theories. The energy required to probe quantum gravitational effects is near the Planck scale, trillions of times higher than what our particle accelerators can reach. We might have to reconcile ourselves to having multiple untestable theories, choosing between them based on mathematical elegance rather than experimental evidence. Item 29. Why does math work? Physicist Eugene Wigner wrote a famous essay in 1960 called The Unreasonable Effectiveness of Mathematics in the Natural Sciences. His question, why does math, which we invent in our minds, describe reality so perfectly? We invented complex numbers to solve equations that had no real solutions. Then physicists discovered that quantum mechanics requires complex numbers. We invented group theory for abstract algebra. Then physicists discovered it's essential for describing particle physics symmetries. Over and over, mathematicians create abstract tools that later turn out to describe real physical phenomena. Is math discovered or invented? Are mathematical truths out there in some Platonic realm, or are they human constructs? And if they're human constructs, why do they work? Think of it like creating a fictional language and then discovering that aliens actually speak it. Item 30. The nature of infinity. Does infinity exist in reality, or only in mathematics? We use infinity constantly in physics. Infinite space, infinite time, infinite density at singularities. But physicist Max Tegmark has argued that physical infinities might be impossible. If they were real, he suggests, it would create absurd situations. For example, in an infinite universe with infinite planets, every possible event would happen infinite times. There would be infinite copies of you reading this right now, and infinite copies making every possible different choice. Some physicists embrace this conclusion. It's called the many worlds interpretation, but others think it proves infinity can't be physically real. Mathematician David Hilbert created a thought experiment called Hilbert's Hotel to show how bizarre infinity is. A hotel with infinite rooms is completely full. A new guest arrives. The manager simply moves the guest in room 1 to room 2, the guest in room 2 to room 3, and so on, leaving room 1 empty. Infinity minus infinity doesn't equal 0. It can equal any number, or even infinity itself, depending on how you do it. Let me pause and remind you, we're halfway through just the first third of mysteries. If your brain isn't hurting yet, you're not paying attention. And here's the thing. Every mystery we've covered so far has one thing in common. They all involve the nature of reality itself. But what about closer to home? What about phenomena on Earth that science can't explain? That's where we're going next. Item 31. Ball lightning. People have reported seeing glowing spheres of light during thunderstorms for centuries. They float through the air, pass through walls, sometimes explode. Scientists dismissed these reports as hallucinations or misidentified regular lightning until pilots, meteorologists, and physicists started reporting them too. In 2014, Chinese scientists accidentally captured ball lightning on video during a lightning storm using high-speed cameras and spectrometers. The spectra showed it contained silicon, iron, and calcium, possibly vaporized soil material. But we still don't know what creates it or sustains it. Plasma shouldn't stay together in a ball for more than milliseconds without a containing magnetic field, yet ball lightning can last for seconds and move independently. Theorist Vladimir Bychkov has proposed dozens of theories: mini black holes, antimatter, microscopic black holes, quantum effects, electromagnetic knots. None fully explain all reported properties. Item 32. The Taos hum. Since the early 1990s, residents of Taos, New Mexico, have reported hearing a persistent low-frequency humming sound. Not everyone hears it, only about 2% of residents. Those who do hear it describe it as maddening, like a diesel engine idling in the distance that never stops. Researchers from various universities investigated with sensitive equipment. They couldn't detect any unusual acoustic signals. Yet the people who hear it aren't making it up. Their distress is real, and they all describe the same sound. Similar hums have been reported in Bristol, England, Largs, Scotland, and Auckland, New Zealand. Theories include industrial equipment, military experiments, electromagnetic radiation, somehow producing sound in people's ears, or even mass tinnitus triggered by environmental factors. But we don't know. The Taos hum remains unexplained. Item 33. The Bermuda Triangle. Okay, you've heard of this one, but hear me out. The myth is that ships and planes mysteriously disappear in the Bermuda Triangle at a higher rate than elsewhere. The reality? The U.S. Coast Guard and other authorities say disappearances there happen at the same rate as anywhere else when adjusted for traffic volume. But here's the actual mystery. Why does the myth persist so strongly? Psychologists can't fully explain why people are drawn to mysterious explanations, even when mundane explanations are more likely. The Bermuda Triangle has become a case study in cognitive bias and how humans process risk and uncertainty. Some disappearances in that region do have unusual features, like Flight 19 in 1945, where 5 torpedo bombers vanished, and the rescue plane sent to find them also disappeared. But the most likely explanation is mundane: bad weather, equipment failure, and human error compounded by the deep, fast-moving waters that quickly disperse wreckage. Item 34. Why migrating animals navigate perfectly sea. Turtles hatch on a beach, swim out to sea, spend 20 years swimming across oceans, then return to the exact same beach where they were born to lay their eggs. How? They don't have maps or GPS. Birds migrate thousands of miles and return to the same tree. Monarch butterflies travel from Canada to Mexico, a journey that takes 4 generations, yet the 4th generation finds the exact same tree their great-great-grandparents left. We know animals use magnetic fields, star positions, smell, and landmarks. But we don't know how they integrate all this information into such precise navigation. Biologist Kenneth Lohman has spent decades studying sea turtle navigation and admits we still don't understand how they create a map in their brain that's accurate enough to find a specific beach from thousands of miles away. Item 35. The origin of life. This is the big one. We have detailed theories about how life evolved once it existed, but we can't explain how it started. The gap between chemicals in water and living cell is enormous. In 1953, the Miller-Urey experiment showed that amino acids, building blocks of proteins, can form naturally from simple chemicals. Great start, but amino acids aren't alive. You need to get from amino acids to self-replicating molecules, to protocells with membranes, to actual cells with metabolism. Each step faces huge obstacles. The RNA world hypothesis suggests RNA came first because it can both store information, like DNA, and catalyze reactions, like proteins. But RNA is fragile and difficult to form spontaneously. Biologist Jack Szostak is trying to create synthetic cells in the lab and admits we're nowhere close. Some scientists, like Francis Crick, co-discoverer of DNA structure, seriously considered panspermia, the idea that life originated elsewhere in the universe and arrived on Earth via meteorites. But that just pushes the question to another planet. Somewhere, somehow, non-living chemistry became biology. We don't know how. Item 36. The Cambrian explosion. For billions of years, life on Earth was simple, single cells and simple multicellular organisms. Then, about 541 million years ago, something extraordinary happened. Over just 15 to 20 million years, a blink in geological time, most major animal groups appeared suddenly. Eyes evolved, shells appeared, predators emerged. Paleontologist Stephen Jay Gould called it the most important evolutionary event in the history of life. But what triggered it? Why did complexity explode so suddenly after billions of years of simplicity? Theories include rising oxygen levels, the evolution of predation forcing an arms race, genetic innovations, a snowball Earth event ending, or even a change in ocean chemistry. But there's no consensus. Some aspect of Earth's environment or biology changed radically, and we're not sure what. Item 37. Why do species go extinct periodically? Earth has experienced 5 mass extinctions, where more than 75% of species died. The most famous killed the dinosaurs 66 million years ago. Asteroid impact. But others are mysterious. The Permian-Triassic extinction, 252 million years ago, killed 96% of all marine species and 70% of terrestrial vertebrates. It's nicknamed the Great Dying. What caused it? Maybe volcanic eruptions, maybe climate change, maybe an asteroid, maybe all 3. We're not sure. And here's what will blow your mind. We might be in the early stages of a 6th mass extinction right now, caused by humans. Species are going extinct at 100 to 1,000 times the background rate. But we don't fully understand the long-term consequences. Ecosystems are complex webs, and removing species can trigger cascading effects we can't predict. Item 38. How eels reproduce. Europeans have eaten eels for thousands of years. But until 1896, nobody had ever seen an eel egg or a baby eel. Scientists didn't know how they reproduced. We now know that European eels migrate thousands of miles to the Sargasso Sea in the Atlantic to spawn. American eels do too. The larvae then drift on currents back to the coasts. But we've never actually observed them mating. We've never seen the eggs in the wild. We've caught mature eels migrating to the Sargasso Sea, and caught young eels migrating back, but the actual reproduction? Never witnessed. Biologist Katsumi Tsukamoto spent decades trying to find where Japanese eels spawn, and only located the spawning area in 2006, after 40 years of searching. But even he's never seen them actually mate. Item 39. How anesthetics affect plants. Here's something bizarre. Anesthetics work on plants. If you anesthetize a Venus flytrap, it won't close when touched. If you anesthetize a Mimosa pudica, a sensitive plant, its leaves won't fold. This was discovered in the 1800s and confirmed with modern anesthetics in recent years. But plants don't have nervous systems. They don't have neurons. They're not conscious, as far as we know. So why do drugs designed to cause unconsciousness in humans also stop plant movement? Are plants more like animals than we realize, or is consciousness less special than we think? Botanist František Balaska argues plants have plant neurobiology, electrical signaling systems that respond to anesthetics. But we don't understand the mechanism or what it means philosophically. Item 40. The Fermi paradox. In 1950, physicist Enrico Fermi asked a simple question over lunch. Where is everybody? If intelligent life is common in the universe, why haven't we detected any signs of it? Our galaxy is billions of years old. Even at slow speeds, a civilization could colonize the entire galaxy in just a few million years. So why don't we see evidence of alien civilizations? This is the Fermi paradox, and proposed solutions are disturbing. 1. We're the first intelligent species, unlikely given the age of the universe. 2. Intelligent life is rare or impossible, but why? 3. Civilizations destroy themselves before becoming detectable. Nuclear war, climate collapse, AI. 4. They exist but are deliberately hiding from us. 5. They exist, but we don't recognize their technology as technology. 6. They existed, colonized everything, then went extinct, and we're living in the ruins. None of these are satisfying. Either we're incredibly special, or something filters out advanced civilizations. Scientist Robin Hansen calls this the Great Filter, some challenge that prevents most life from becoming spacefaring. The terrifying question: is the Great Filter in our past, we're the lucky ones who survived, or in our future, we're about to hit it? You're probably starting to notice a pattern. Science has incredible explanatory power for many things, but at the boundaries of knowledge, mysteries pile up. We understand a lot about how, but almost nothing about why. And we're about to get even stranger, because the next section explores phenomena that seem to violate the laws we're most confident about. Item 41. Why the sun's corona is hotter than its surface. Surface of the sun is about 500 degrees Celsius. Reasonable. But the corona, the sun's atmosphere extending millions of kilometers into space, is over 1 million C. That violates thermodynamics. Heat doesn't naturally flow from cold to hot. It's like holding a torch and discovering that your hand is cooler than the flame, but the air 3 feet above the flame is hotter than the flame itself. We've proposed mechanisms: magnetic reconnection, plasma waves, nanoflares. But NASA's Parker Solar Probe, which is literally flying through the corona right now, still hasn't given us a complete answer. We know energy is being transferred somehow, but the exact mechanism that heats the corona to these extreme temperatures remains unclear. Item 42. Fast radio bursts. In 2007, astronomer Duncan Larimer discovered something in archived radio telescope data. A blast of radio waves lasting just milliseconds, but releasing as much energy as the sun emits in a day. These fast radio bursts, FRBs, come from distant galaxies, billions of light years away. We've now detected hundreds of them. Most happen once and never repeat. A few repeat on unpredictable schedules. Some have strange patterns. One pulses every 157 days. What causes them? Theories include colliding neutron stars, black holes consuming pulsars, magnetar eruptions, or even aliens sending signals, though that's the least likely. In 2020, we finally detected an FRB from within our own galaxy, confirming that at least some come from magnetars. But we still don't understand the mechanism, and some FRBs might have completely different origins. Item 43. The WOW signal. On August 15, 1977, astronomer Jerry Emmon was reviewing data from the Big Ear radio telescope when he saw something that made him write, "Wow," in the margin. A strong narrowband radio signal had been detected lasting 72 seconds, exactly what you'd expect from an intelligent transmission. The signal came from the direction of Sagittarius, was at 1,420 megahertz, the frequency hydrogen emits at, which aliens might use to signal, and has never been detected again despite decades of searching. Astronomer Antonio Parris proposed in 2017 that it was caused by a comet, but other scientists disputed this, pointing out the signal's characteristics don't match cometary emissions. We simply don't know what it was. It remains the most intriguing unexplained signal SETI has ever detected. Item 44. Why galaxies form spirals. Look at pictures of galaxies. Many are beautiful spirals. But here's the problem. Galaxies rotate, and the outer parts rotate more slowly than the inner parts, like a record on a turntable. This means spiral arms should wind up and disappear within a few rotations. But they don't. Spiral galaxies billions of years old still have clear spiral structure. Why? The current explanation involves density waves. The spiral pattern isn't made of the same stars all the time, but rather is a wave of compression moving through the galaxy, like a traffic jam on a highway. Stars move into the jam, slow down, making the spiral appear bright, then move out. But this theory has problems. It doesn't explain all observed spiral patterns, and it requires a triggering mechanism we haven't fully identified. Astrophysicist Frank Hsu developed much of the density wave theory in the 1960s, but even he acknowledged it was incomplete. Item 45. The cold spot in the cosmic microwave background. The cosmic microwave background, CMB, is the afterglow of the Big Bang, radiation filling the entire universe. It's remarkably uniform, with temperature variations of only a few millionths of a degree, except for one region, the cold spot. Discovered in 2004, the cold spot is about 70 microkelvin colder than average and spans about 5 degrees of sky, 10 times the moon's width. The odds of such a large cold region existing by random chance? About 1 in 50. Unlikely, but not impossible. But some cosmologists think it might be evidence of something more exotic. A collision with another universe, a supervoid, a massive region with less matter, or even a sign that the universe has weird topology, like a cosmic dent. We don't know, and the answer could tell us something fundamental about cosmology. Item 46. Why Uranus and Venus rotate backwards. Every planet in our solar system spins in the same direction, except Uranus and Venus. Uranus is tilted on its side, rotating at a 90-degree angle. Venus rotates backward and incredibly slowly. One day on Venus is longer than 1 year on Venus. The standard explanation is catastrophic collisions early in the solar systems. History knocked them into weird rotations, but the details don't add up perfectly. For Venus, a collision big enough to reverse its rotation should have left evidence in its geology or obliterated it entirely. For Uranus, the tilt is so extreme that the collision must have been massive, yet Uranus's moons rotate in the same plane, which shouldn't happen if the collision happened after the moons formed. Some planetary scientists think tidal interactions or migration through a debris disk could explain these rotations without impacts, but there's no consensus. Item 47. The moon's origin. The leading theory is the giant impact hypothesis. About 4.5 billion years ago, a Mars-sized object called Theia collided with Earth. The debris coalesced into the moon. This explains many observations. The moon's composition is similar to Earth's mantle. It's unusually large relative to Earth, and it has little iron, but there are problems. Computer simulations suggest the moon should be mostly made of Thea's material, not Earth's. Yet isotope analysis shows the moon and Earth have nearly identical chemical signatures. Some variants of the theory propose that both Earth and Theia were already similar in composition, or that the impact vaporized both so thoroughly that they mixed. But we're not certain. Planetary scientist Robin Carnap has refined the models over decades, but she admits, we still don't have a perfect model that explains everything. Item 48. Plate tectonics on Earth alone. Earth has plate tectonics. The crust is broken into pieces that move, dive under each other, and recycle. This is essential for life. It regulates climate by controlling carbon dioxide levels and creates diverse environments. But as far as we know, no other rocky planet has active plate tectonics. Venus, Mars, Mercury, they all have solid, unbroken crusts. Why is Earth special? We're not sure. Maybe Earth's water lubricates the crust. Maybe the moon's tidal forces play a role. Maybe it's just chance. But plate tectonics seems to be a rare phenomenon, and we don't fully understand what makes it possible. Item 49. Why Earth's core is still hot. Earth's core is about 60 degrees Celsius, as hot as the surface of the sun. But Earth is 4.5 billion years old. Why hasn't it cooled down? Leftover heat from Earth's formation and radioactive decay provide some heat, but calculations suggest Earth should have cooled more than it has. Some geophysicists think we're missing a heat source. Maybe there's more radioactive material in the core than we thought. Maybe there are exotic nuclear reactions happening under extreme pressure. Or maybe our models of heat transfer in the mantle are wrong. We can't dig down to the core to check. The deepest hole ever drilled barely scratched the crust. Item 50. The mystery of Earth's water. Where did Earth's water come from? Earth formed close to the sun, where temperatures were too high for water to condense. So all of Earth's water must have been delivered from elsewhere, likely by asteroids and comets after Earth formed. But isotope analysis throws a wrench into this. Water has different flavors depending on the ratio of hydrogen to deuterium, heavy hydrogen. Comets have the wrong ratio to match Earth's oceans. Most asteroids have a closer match, but not perfect. Some of Earth's water might have been trapped in minerals during formation, then released later. Planetary scientist Tobias Owen has studied this for decades and concludes, we still don't have a complete story. Here's where things get personal. We've been talking about cosmic mysteries and planetary oddities. But what about the mysteries affecting your everyday experience? What about the things that happen to you that science can't explain? That's what's next. And trust me, this is where it gets really strange. Item 51. Why do we forget dreams? You wake up from a vivid dream, convinced you'll remember it. 5 minutes later, it's gone. Dreams fade faster than any other memory. Why? We remember emotionally significant events for years, but detailed dreams, even vivid, emotional ones, vanish within minutes. Neuroscientist Mark Solms suggests it's because the brain regions responsible for storing long-term memories are less active during dreaming. But that doesn't explain why we sometimes remember dreams from decades ago, but forget last night's dream instantly. Some researchers think dream amnesia is protective. If we remembered all dreams vividly, we'd confuse dream memories with real memories. But this is speculation. Item 52. Why music gives us chills. When you hear certain songs, you get chills. A tingling sensation, goosebumps, hair standing on end. About 50% of people experience this. Neuroscientist Robert Zatorre has studied it extensively using brain imaging. Music activates the same reward pathways as food and sex. Your brain releases dopamine. But here's the mystery. Why? Music has no survival value. It doesn't feed us or help us reproduce. Why would evolution wire our brains to find patterns of sound intensely pleasurable? Some evolutionary psychologists argue music evolved as a social bonding mechanism or a way to demonstrate cognitive fitness to potential mates. But these are just so stories. We have no evidence. The honest answer is, we don't know why music makes us feel emotion so powerfully. Item 53. Why do we laugh? Laughter is universal to humans. Every culture laughs. But why? The standard explanation is that humor helps us bond socially and relieve tension. Okay, but that doesn't explain the mechanism. Why do surprising incongruities trigger a specific involuntary vocalization? Neuroscientist Robert Provine recorded thousands of laugh episodes and found that most laughter doesn't occur in response to jokes. Most laughter happens during normal conversation after banal statements like, "I'll see you later." We laugh more at social cues than at comedy. So maybe laughter is a social signal, like smiling. But that still doesn't explain why certain cognitive patterns, like incongruity or surprise, trigger it. Philosopher John Muriel has proposed dozens of theories: relief theory, superiority theory, incongruity theory, but none fully explains laughter. Item 54. Near-death experiences. People who come close to death sometimes report vivid experiences: seeing a tunnel of light, encountering deceased relatives, feeling immense peace, experiencing their life flashing before them. Skeptics attribute these to oxygen deprivation, endorphins, or hallucinations as the brain shuts down. But here's the problem. Some people report near-death experiences during cardiac arrest when their brain shows no electrical activity. Cardiologist Piam van Lommel conducted a study of cardiac arrest survivors and found that about 18% reported detailed memories from a period when they were clinically dead. How can you form memories when your brain isn't functioning? Materialist scientists argue the experiences must occur during the moments before or after unconsciousness, and the person's sense of timing is distorted. But some details are hard to explain, like patients reporting events they couldn't have witnessed, like conversations in other rooms. I'm not saying NDEs are proof of an afterlife, but they're genuinely unexplained. We don't know why these specific experiences occur so consistently across cultures, or how they're formed neurologically. Item 55. Savant syndrome. Some people with developmental disorders have extraordinary abilities in narrow domains. Stephen Wiltshire can draw detailed cityscapes from memory after a single helicopter ride. Daniel Tammet can recite pi to 22,500 digits and learned Icelandic in 1 week. Kim Peek, inspiration for Rain Man, memorized over 12,000 books. But here's the mystery. How? Their brains aren't larger or fundamentally different. Some savants acquire abilities after brain injuries. A blow to the head suddenly gives them the ability to play piano or speak a language they never studied. Neuroscientist Daryl Trefford has studied savants for decades and proposes that their brains access information processing that normally occurs unconsciously. The rest of us have these abilities too, but they're buried beneath layers of higher cognitive function. Brain damage or developmental differences might release these abilities by reducing inhibition, but we don't really understand it. Why would evolution hide extraordinary abilities behind cognitive barriers? Item 56. Synesthesia. About 4% of people have synesthesia, when one sense automatically triggers another. The most common type is grapheme color synesthesia. People see specific colors when they see letters or numbers. The letter A might always appear red, B might appear blue, and so on. Other types include seeing colors when hearing music, tasting words, or perceiving time as spatial locations. Synesthesia is consistent for each person. Their A is always the same red and runs in families, suggesting a genetic component. But why does it exist? Neuroscientist V.S. Ramachandran proposes that nearby brain regions for different senses have extra connections in synesthetes, cross-wiring that creates unusual associations. But that doesn't explain why specific associations form, or what evolutionary purpose, if any, synesthesia serves. Item 57. Why do we have music and art? No known human culture lacks music and art. This suggests they're not random cultural inventions, but deeply rooted in human nature. But why? Music and visual art have no obvious survival value. Evolutionary psychologists have proposed theories. Art demonstrates skill to attract mates. Music helps groups coordinate. Creating art releases pleasure chemicals that reinforce social bonding. But these are speculations. The fact remains that humans spend enormous time and resources creating things that don't help us survive. Philosopher Dennis Dutton argued in The Art Instinct that art might be a byproduct of other cognitive abilities, our pattern recognition, social cognition, and imagination. We didn't evolve to make art. We evolved brains capable of making art as a side effect. But even this doesn't explain why art feels meaningful to us. Item 58. Phantom limb syndrome. People who lose limbs often feel the missing limb is still there. They feel pain, itching, or movement in fingers that don't exist. This is called phantom limb syndrome, and it can be agonizing. Neuroscientist V.S. Ramachandran developed a famous treatment, the mirror box. Patients place their intact limb in a box with mirrors, so it appears they have both limbs. Moving the intact limb while watching the mirror can relieve phantom pain. Somehow, visual feedback overrides the phantom sensations. But why do phantom limbs occur at all? The brain has a body map, a representation of where your limbs are. When you lose a limb, the map doesn't update completely. The brain still sends signals to the missing limb and interprets lack of feedback as pain. But why wouldn't the brain adapt? People who are born without limbs don't experience phantoms. Only people who had limbs and lost them. The brain's body map is surprisingly rigid. Item 59. Why do we point? You point at something, and another person looks where you're pointing. This seems trivial, but it's not. Chimpanzees, our closest relatives, don't point to show things to each other, though they can learn to understand human pointing. Pointing requires understanding that another being has a different perspective and can direct their attention. Developmental psychologist Michael Tomasello has studied this extensively. Babies start pointing around 12 months old, before they can speak complex sentences. Pointing isn't taught. It emerges naturally. This suggests it's a uniquely human cognitive adaptation. But why did we evolve it? Pointing must have provided enormous social advantages, sharing information, coordinating action. But the cognitive leap required is significant. You have to understand. 1. Others have minds. 2. They can attend to things. 3. You can influence their attention. That's theory of mind, and we don't fully understand how it evolved. Item 60. The cocktail party effect. You're at a noisy party with dozens of conversations happening. Somehow, you can focus on one conversation and tune out the rest. But the moment someone across the room says your name, you hear it immediately. This is the cocktail party effect, and we don't fully understand how the brain does it. Your ears are receiving all the sound, but your brain filters it in real time, prioritizing relevant information and suppressing background noise. Computer algorithms struggle to do this. Source separation in noisy environments is an unsolved problem in AI. Cognitive psychologist Donald Broadbent proposed in the 1950s that the brain has a selective attention filter, but that doesn't explain how the filter knows what's relevant. Your name is relevant, so the filter lets it through. But how does the filter identify your name in a word it's supposedly filtering out? It's a paradox. Okay, step back for a moment. We're 1 hour in, and you've learned that science can't explain your consciousness, dreams, laughter, music, or how you pay attention. These are everyday experiences, and we have no idea how they actually work. Starting to feel like we don't know as much as we thought? Good, because now we're diving into biological mysteries that are going to make you question what life even means. Item 61. Tardigrades' indestructibility. Tardigrades, tiny water bears, can survive nearly anything. They can endure temperatures from near absolute zero to 150 degrees Celsius. They can survive pressures 6 times greater than the deepest ocean trenches. They can withstand 1,000 times more radiation than humans. They can survive in the vacuum of space. When conditions get harsh, tardigrades enter cryptobiosis. They dry out completely, expel all water, and shut down their metabolism. They can remain in this state for decades, then revive when exposed to water. In 2016, a tardigrade frozen in Antarctic ice for 30 years was revived, but we don't understand how they do it. How does an organism survive with no water? Cells need water to function. Biologist James Fleming discovered that tardigrades produce unique proteins that form glass-like structures protecting their cells. But we don't know how these proteins work or why tardigrades evolved such extreme resilience. Item 62. How octopuses think. An octopus has 500 million neurons, about the same as a dog, but 2/3 of them are in its arms, not its brain. Each arm can act independently, solving problems without consulting the brain. An octopus arm can search a crevice while the octopus focuses elsewhere. But here's the truly strange part. Octopuses are colorblind, yet they change color to match their surroundings with astonishing accuracy. Biologist Roger Hanlon has studied this for decades. His theory? Octopus skin can see light directly without using the eyes. Skin cells contain the same light-sensitive proteins, opsins, found in eyes. So an octopus's skin detects color and changes to match it, all without the brain's involvement. It's distributed intelligence. If you cut off an octopus arm, it will continue reacting to stimuli for hours. The arm is partially conscious without the body. Item 63. Zombie cells. As you age, some of your cells stop dividing but don't die. They enter senescence. They're not alive in the normal sense, but not dead either. They just exist, releasing inflammatory chemicals. These are called zombie cells or senescent cells. Biologist Judith Campisi discovered that these cells contribute to aging and age-related diseases. When researchers removed senescent cells from mice, the mice lived 30% longer and stayed healthier. Pharmaceutical companies are now developing senolytic drugs to eliminate zombie cells in humans. But here's the mystery. Why do cells become senescent instead of just dying? It might be an anti-cancer mechanism. Damaged cells enter senescence instead of dividing uncontrollably. But if so, why do senescent cells harm the organism long term? Evolution should have found a better solution. Item 64. Why do we age? This should be simple, right? Wear and tear. But many organisms don't age the way we do. Lobsters don't age. They keep growing, and their cells don't show signs of deterioration. Hydras, tiny freshwater organisms, are biologically immortal. Some trees live for thousands of years. So aging isn't inevitable. It's specific to certain organisms. Evolutionary biologist Peter Medawar proposed in the 1950s that aging evolved because natural selection is weaker at older ages. Once you've reproduced, there's less evolutionary pressure to keep you alive. But this doesn't explain why some organisms avoid aging entirely. Biologist Aubrey de Grey thinks aging is an engineering problem with a solution. He's identified 7 categories of cellular damage that cause aging and proposes we can fix them. But other biologists think aging might be programmed, a feature, not a bug. We're not sure which is correct. Item 65. Quantum biology. Quantum effects supposedly only matter at ultra-small scales and ultra-cold temperatures. Biology is warm, wet, and messy. Quantum effects should be irrelevant, but they're not. Photosynthesis is nearly 100% efficient at converting light to chemical energy. Classical physics can't explain this. But in 2007, researchers discovered that photosynthesis uses quantum coherence. Light energy exists in multiple pathways simultaneously, and the plant samples all pathways to find the most efficient one. This is quantum superposition happening in a warm leaf. Birds navigate using Earth's magnetic field. Biologist Klaus Schulten proposed in the 1970s that this involves quantum entanglement in proteins in birds' eyes. For decades, this seemed absurd. But in 2021, researchers found evidence supporting it. If quantum effects matter in biology, it could explain mysteries like consciousness, mutation rates, and enzyme efficiency. But it raises a philosophical problem. If your brain uses quantum effects, you might not be entirely deterministic. Quantum randomness could mean you have genuine free will, or it could mean your thoughts are partially random. We don't know. Item 66. The wow mechanism of photosynthesis. Expanding on the previous item, plants convert sunlight to chemical energy with an efficiency classical chemistry says is impossible. When light hits a photosynthetic complex, it has to travel from the point of absorption to the reaction center where energy is stored. According to classical physics, energy should bounce around randomly, losing efficiency. But experiments show energy takes multiple paths simultaneously and chooses the most efficient one. This is quantum coherence. The energy exists in a superposition of all possible paths until it collapses into the reaction center. Chemist Graham Fleming discovered this in 2007. His team cooled photosynthetic complexes to cryogenic temperatures, expecting quantum effects to appear. Then they tested room temperature and found the effects persisted. Quantum coherence in warm, wet biology shouldn't be possible. But it is. Item 67. How cells know where they are. During embryo development, cells differentiate into different types: skin, muscle, neurons, liver. But every cell has the same DNA. So how does a cell know whether to become a heart cell or a brain cell? The answer involves chemical gradients. Cells respond to their position in chemical concentration fields. But that just pushes the question back. How do cells interpret gradients so precisely that they build a functioning organism? Developmental biologist Lewis Wolpert called this positional information, but we don't understand it fully? Computer scientist Alan Turing. Yes, the Turing test guy proposed in 1952 that patterns emerge from reaction diffusion systems, chemicals. Spreading and reacting create stable patterns. His equations explain animal stripes and spots. But embryonic development is more complex than patterns. Its construction following a blueprint encoded nowhere except in chemical interactions. Item 68. Metamorphosis. A caterpillar builds a chrysalis, dissolves into cellular soup, then reorganizes into a butterfly. How? The caterpillar's body produces enzymes that break down most tissues. But some cells, imaginal discs, survive and use the dissolved material to build butterfly structures. But here's what blows my mind. Some memories survive metamorphosis. Researcher Martha Weiss trained caterpillars to avoid certain smells by giving them mild electric shocks. After metamorphosis, the butterflies still avoided those smells. Memories persisted despite the brain being mostly dissolved and rebuilt. How is information encoded in a way that survives such radical transformation? We don't know. Item 69. How viruses originated. Viruses are strange. They're not alive. They can't reproduce without hijacking a cell. But they're not inert chemicals either. They evolve, adapt, and have genetic material. Where did they come from? Three main theories. 1. They're ancient, predating cells. 2. They're degenerate cells that became parasitic. 3. They're escaped genetic material from cells. But we have no fossil record of viruses. They don't fossilize. So we're guessing based on genetic comparisons. Some virologists think viruses might have played a crucial role in the origin of life itself. They're simpler than cells and might represent an early stage in biological complexity. But this is speculation. Item 70. Prions. Prions are misfolded proteins that cause other proteins to misfold. They're infectious like viruses, but contain no DNA or RNA, just protein. They cause diseases like mad cow disease and Creutzfeldt-Jakob disease in humans. How can a protein be infectious? The prion shape is more stable than the normal protein shape, so contact causes normal proteins to refold into the prion shape. It's like a shape contagion. Stanley Prusiner won the Nobel Prize in 1997 for discovering prions, and it was controversial because the idea seemed impossible. But here's the truly weird part. Some researchers think memories might be stored partially as prion-like proteins. Normal memory involves changes in neuron connections, but proteins with prion-like properties could also store information. If this is true, memory is even more mysterious than we thought. Let's take a breath. You're almost 90 minutes into this journey, and we've covered consciousness, quantum physics, alien silence, biological mysteries, and zombie cells. Your conception of reality has probably shifted. You're realizing that the world you thought was well understood is actually deeply strange. But now we're entering the most unsettling section. Things that make you question whether we're asking the right questions at all. Item 71. The simulation hypothesis philosopher Nick Bostrom proposed in 2003 that at least one of three statements must be true. 1. Civilizations go extinct before achieving the ability to run realistic simulations. 2. Advanced civilizations choose not to run simulations. 3. We're almost certainly living in a simulation. His reasoning: if civilizations survive and choose to run simulations, they'll run trillions of them. So the ratio of simulated beings to real beings would be trillions to 1. Statistically, you're probably in a simulation. Tech entrepreneur Elon Musk has stated he thinks there's a 1 in billions chance we're in base reality. But here's the problem. We can't test it. If we're in a simulation, the simulators could hide any evidence. And if we're not in a simulation, we can't prove it. Some physicists think quantum mechanics weirdness, like the universe only rendering details when observed, suggests simulation. But others think this is unfalsifiable philosophy, not science. Item 72. The holographic principle. In the 1990s, physicists Gerard T. Hooft and Leonard Susskind proposed something insane. The universe might be a hologram. All the information about a 3D region of space can be encoded on a 2D surface surrounding it. This came from studying black holes. The information content of a black hole is proportional to its surface area, not its volume. That's strange. Normally, information capacity should depend on volume, like how a bigger hard drive stores more data. But black holes suggest information is fundamentally 2D, and 3D space is the projection. If the holographic principle is true, everything you experience, depth, volume, solidity, is a projection from a 2D information surface. You're not a 3D being. You're a 2D pattern that experiences itself as 3D. We have some mathematical evidence for this from string theory, but we can't test it experimentally. It remains a beautiful idea that might be completely wrong. Item 73. The Mandela Effect. Large groups of people remember historical events differently than the evidence shows. For example, many people remember Nelson Mandela dying in prison in the 1980s. He didn't. He died in 2013. Many people remember the Berenstain Bears being spelled Berenstein. Many people remember a movie called Shazam, starring comedian Sinbad. No such movie exists. The psychological explanation is confabulation, false memories created when the brain fills gaps. We're terrible at remembering details accurately. But what's weird is how specific and consistent these false memories are across many people. Some people seriously propose explanations like parallel universes or timeline shifts. These are nonsense. But the phenomenon itself, mass-consistent false memory, is genuinely interesting psychologically and still not fully understood. Item 74. Why is there no unified theory? We have quantum mechanics for the small, general relativity for the large, and they contradict each other. For a century, physicists have tried to unify them. String theory was promising, but has made no testable predictions in 50 years. Loop quantum gravity is an alternative, but also lacks experimental support. Some physicists are starting to wonder, what if there is no unified theory? What if reality is fundamentally divided into incompatible domains? Physicist Freeman Dyson suggested that the universe might be too clever for humans to understand fully. This is unsettling. Science assumes reality is comprehensible. If it's not, if the universe is inherently beyond human understanding, then we'll hit a wall. We might be like dogs trying to understand calculus. Item 75. The nature of mathematics is math invented or discovered? Platonists believe mathematical truths exist independently, and we discover them like discovering a mountain. Formalists believe math is a human invention, like inventing a game with rules. If math is discovered, where do mathematical objects exist? In what sense does the number pi exist? It's not a physical object, yet it has definite properties. If math is invented, why does it describe reality so perfectly? Why do equations physicists write down in their offices turn out to predict phenomena they've never observed? Mathematician Roger Penrose believes in 3 worlds: the physical world, the mental world, and the Platonic world of mathematical forms. But he admits we don't understand how these worlds interact. Item 76. Consciousness in animals. Your dog seems conscious. It feels pain, joy, fear. But how do you know? You can't experience your dog's subjective experience. Philosopher Thomas Nagel wrote a famous essay, "What is it like to be a bat?" arguing we can never truly know. But here's where it gets weirder. Is a fish conscious? An insect? A bacterium? Where's the line? Some philosophers think consciousness is binary. You either have it or don't. Others think it's a spectrum. Neuroscientist Christoph Koch suspects even very simple systems might have rudimentary consciousness. Panpsychism, the idea that consciousness is a fundamental property of matter, is making a comeback among some scientists. But we have no way to test this. We can't measure consciousness directly. We only know we have it through direct experience. Item 77. The combination problem. If panpsychism is true, if electrons and quarks have tiny bits of consciousness, how do they combine to create a unified conscious experience? This is called the combination problem. Your brain has 86 billion neurons. If each neuron has its own micro-consciousness, why don't you experience 86 billion separate consciousnesses? How do they merge into one unified you? Think of it like this. If I take 1,000,000,000,000 barely conscious particles and arrange them in a brain, why does a new, larger consciousness emerge? Why not just 1,000,000,000,000 separate tiny consciousnesses? Philosopher William James discussed this in the 1890s. We're no closer to solving it. It might be the hardest problem in philosophy. Item 78. Free will. Do you have free will? It feels like you do. But neuroscientist Benjamin Libet did experiments in the 1980s showing that your brain makes decisions before you're consciously aware of deciding. He measured brain activity, their readiness potential, up to several seconds before subjects reported deciding to act. This suggests your consciousness is just observing decisions your unconscious brain already made. You feel like you're deciding, but you're just narrating decisions that happened unconsciously. But wait, other researchers have questioned Libet's interpretation. Maybe the readiness potential isn't a decision, but preparation. Maybe consciousness is more integrated with unconscious processes than we realize. Philosopher Daniel Dennett argues that the question itself is confused. Free will, as popularly understood, the ability to have done otherwise in identical circumstances, is incoherent. But we can still have a meaningful kind of freedom based on our reasons and desires. We don't have an answer. And the answer matters. It affects how we think about morality, justice, and responsibility. Item 79. The problem of other minds. How do you know other people are conscious? You assume they are because they act like you, and you're conscious. But maybe they're philosophical zombies, beings that act conscious, but have no inner experience. They say, ouch, when pinched, not because they feel pain, but because their programming makes them say it. You can never prove other people are conscious. You only have access to your own consciousness. This is called the problem of other minds, and it's technically unsolvable. Most of us resolve it pragmatically. We assume others are conscious because the alternative is solipsism. Only you exist. But logically, we can't prove it. Item 80. Self-awareness, you're aware of being aware. This is meta-consciousness. Consciousness reflecting on itself. Very few animals have it. The mirror test. An animal recognizes itself in a mirror, suggests self-awareness. Chimpanzees, dolphins, elephants, and magpies pass. Most animals don't. But what generates self-awareness? Why isn't first-order consciousness experiencing things enough? Why did evolution add this meta layer? Psychologist Michael Graciano proposes that self-awareness is a model the brain creates to predict its own behavior. You have a mental model of yourself, the same way you have mental models of other people. But why would evolution create a model of yourself that includes subjective experience? No answer yet. We're at the 90-minute mark. Let me ask you something. How do you feel right now? Disoriented? Overwhelmed? Like the ground has shifted under you? Good. That means you're paying attention, because the truth is, we're surrounded by mystery. Science is incredible. It's given us technologies and knowledge beyond ancient imagination. But at the boundaries, we're still in the dark. And the next 30 mysteries are going to get even more personal, because they're about society, history, and humanity itself. Item 81. Why did humans suddenly start building civilizations? For 200,000 years, humans were hunter-gatherers. Then, about 10,000 years ago, we suddenly started farming, building cities, and creating complex societies. Why? What changed? The standard explanation: we learned agriculture. But that just pushes the question back. Why did we learn agriculture then? Climate got warmer after the last ice age, but humans had survived warming periods before without becoming agricultural. Archaeologist James C. Scott argues in Against the Grain that early agriculture was actually worse for human health than hunting and gathering. Early farmers were shorter, more diseased, and worked harder than their hunter-gatherer ancestors. So why did people adopt it? Some theories. Population pressure forced it. Religion motivated it. Temples like Göbekli Tepe predate agriculture. Or it was an accident. People who stayed near wild grain developed sedentary habits. But we don't know. Item 82. The collapse of Bronze Age civilizations. Around 1200 BCE, several major civilizations collapsed simultaneously. The Hittites, Mycenaeans, Egyptians, weakened, and many city-states in the Near East. This is called the Late Bronze Age collapse, and it's mysterious. Theories include invasion by sea peoples, earthquakes, drought, systems collapse, trade networks were so interconnected that one failure cascaded, or internal rebellion. But no single theory explains why civilizations hundreds of miles apart all collapsed at the same time. Archaeologist Eric Klein has written extensively about it and concludes it was probably a perfect storm of multiple factors. But that's not satisfying. We'd like to understand what causes civilizational collapse. It's relevant to our own future. Item 83. Why did the Industrial Revolution happen in Europe? China was more technologically advanced than Europe for centuries. Gunpowder, paper, printing, compass, all Chinese inventions. So why did the Industrial Revolution happen in 18th century Britain instead of China? Historian Kenneth Pomerantz calls this the Great Divergence. Explanations include Europe's fragmented politics encouraged competition. Coal deposits were near population centers. Colonialism provided resources and markets. Or cultural factors, Protestantism, Enlightenment values, encouraged innovation. But none fully explain it. And it matters. The Industrial Revolution shaped the modern world. Understanding why it happened could inform how we think about innovation and development today. Item 84. Why did Neanderthals go extinct? Neanderthals survived for 300,000 years, longer than modern humans have existed. They had larger brains, stronger bodies, and sophisticated tools. Then, around 40,000 years ago, they went extinct shortly after modern humans arrived in Europe. Did humans kill them? Unlikely. There's little evidence of violence. Did we outcompete them for resources? Maybe. Did diseases we carried wipe them out? Possibly. Did we interbreed until they disappeared as a distinct group? DNA evidence shows modern humans interbred with Neanderthals. Most people have 1 to 2% Neanderthal DNA, but that doesn't explain total extinction. Anthropologist Clive Finlayson suggests climate change was the key factor. Neanderthals were adapted to specific environments that vanished. But why did humans survive the same climate changes? Item 85. The Indus Valley Script. The Indus Valley civilization flourished from 3,300 to 1300 BCE in what's now Pakistan and India. They built cities, traded extensively, and used a writing system, but we can't read it. We have over 4,000 inscriptions, but they're short, averaging 5 signs. We don't know what language they spoke, so we can't use linguistic clues to decode it. Some researchers think it's not writing at all, but rather symbolic or ritualistic marks. Archaeologist Asko Parpilla has spent decades trying to decipher it. He thinks it's related to Dravidian languages. But without a bilingual inscription, like the Rosetta Stone, we might never know. Item 86. Göbekli Tepe's purpose. Göbekli Tepe in Turkey is a megalithic site dated to 9600 BCE, before agriculture, before pottery, before metalworking. Hunter-gatherers built massive stone circles with intricate carvings. Why? It must have required enormous labor, hundreds of people working for years. But hunter-gatherers were supposed to be nomadic, living hand to mouth. How did they organize and feed a workforce? Archaeologist Klaus Schmidt, who excavated it, thought it was a religious sanctuary that pilgrims visited. But we don't know what religion or why hunter-gatherers would build such a place. Some researchers now think Göbekli Tepe drove agricultural development. The need to feed people gathering there motivated domestication of plants and animals. Item 87. The Fermi Paradox, revisited with sociological angle. We talked about the Fermi Paradox earlier from a scientific angle. But there's a sociological aspect. Maybe civilizations destroy themselves before becoming spacefaring. Nuclear war, climate collapse, AI disaster, bioweapons. We've developed multiple ways to cause our own extinction. And we're not good at long-term thinking. We build systems that work for decades, but fail over centuries. Robin Hansen's Great Filter might be ahead of us. If so, solving it is the most important thing humanity will ever do. But we don't know what the filter is or how to pass it. Item 88. Why humans have whites in our eyes. Most animals have dark eyes. You can't tell where they're looking. Humans have white sclera surrounding our iris, making our gaze direction obvious. Why would evolution advertise where we're looking? Anthropologist Michael Tomasello suggests it's because humans are uniquely cooperative. We use eye contact to communicate and coordinate. Making eye gaze visible helps us work together. But this seems risky. Wouldn't predators benefit from knowing where you're looking? Maybe, but the cooperative advantages outweighed the risks. Or maybe it's a byproduct of something else. We're not sure. Item 89. The origin of language. Language is universal to humans. Every culture has language, and children learn it effortlessly without formal instruction. Linguist Noam Chomsky proposed that humans have an innate universal grammar, a mental structure, specifically for language. But how did language originate? Gradual evolution from simple calls to complex grammar? Or sudden emergence of grammatical ability through a genetic mutation? Anthropologist Robin Dunbar thinks language evolved for social bonding, replacing grooming in large groups. Linguist Derek Bickerton thinks it emerged suddenly to handle displaced reference, talking about things not present. We don't know. The frustrating part? Language doesn't fossilize. We have no direct evidence of early language. We're reconstructing it from modern languages, anatomy, local tracks, and genetics. The FOXP2 gene is implicated, but it's guesswork. Item 90. Why humans are fascinated by stories. Every culture tells stories. Myths, legends, novels, movies. Narrative is universal. Cognitive scientist Mark Turner argues that narrative is how humans think. We understand everything as stories with agents, goals, and consequences. But why? Psychologist Jerome Bruner suggested stories help us simulate social situations, preparing us for real interactions. Evolutionary psychologist Brian Boyd argues stories are mental play, practicing social and survival skills in imagination. But these are speculations. We don't know why humans find narrative so compelling. It might be a deep feature of how our brains organize information. All right, let's pause here. We're 2 hours in, and we've journeyed from consciousness to quantum mechanics to civilizational collapse. You're probably exhausted. But stick with me. We've got one final hour, and it's going to connect everything. Because here's what you need to understand. All these mysteries aren't bugs in our understanding. They're features of reality. The universe is stranger and more beautiful than our ancestors imagined. And you, yes, you are part of this cosmic mystery. Item 91. The future of human evolution. We're still evolving. Genetic studies show recent changes. Lactose tolerance spreading in dairy farming cultures, high-altitude adaptations in Tibetans, resistance to certain diseases. But are we evolving toward anything? Biological anthropologist Peter Ward thinks modern humans might be devolving in some ways. Modern medicine allows people with genetic disorders to survive and reproduce, reducing natural selection pressure. But cultural evolution is accelerating. We're changing our environment faster than biology can adapt. Some futurists think we'll merge with technology, becoming cyborgs. Others think genetic engineering will let us direct our own evolution. But predicting evolution is impossible. It's shaped by unpredictable environmental pressures. Item 92. Why we explore. Humans explore. We crossed oceans in fragile boats, trekked across continents, and launched ourselves into space. Why? Exploration is dangerous, and most explorers find nothing useful. Yet we do it anyway. Psychologist Marvin Zuckerman identified sensation-seeking as a personality trait. Some people need novelty and risk. But exploration is more than thrill-seeking. It's about discovery, curiosity, pushing boundaries. Maybe it's an evolutionary adaptation. Groups that explored found new resources. But exploring requires sacrificing security. It's a gamble. Why do some individuals and cultures gamble more than others? Item 93. The Fermi Paradox. Final take. Let's return to this one last time with a chilling thought. Maybe we don't see alien civilizations because something prevents them from lasting. Physicist John von Neumann proposed self-replicating machines that could spread across the galaxy. If any civilization created these, they'd colonize everything. The fact that we don't see them suggests 1. No one creates them, or 2. Something destroys civilizations before they create them. Maybe the great filter is AI. Maybe advanced civilizations create superintelligent AI that either destroys them or makes them irrelevant. Or maybe it's environmental collapse. Every civilization exhausts its planet's resources. Whatever the filter is, we're approaching it. The next century will determine if humanity survives. Item 94. The heat death of the universe in the far future. Trillions of years. The universe will reach maximum entropy. All stars will burn out. All black holes will evaporate via Hawking radiation. The universe will be cold, dark, and uniform. Nothing will happen because there will be no energy gradients to drive processes. This is called heat death. It's the ultimate fate of the universe, according to thermodynamics. But here's a thought. In an infinite universe with infinite time, quantum fluctuations could eventually, after unimaginable timescales, create random orderings that look like new Big Bangs. Physicist Roger Penrose calls these Boltzmann grains, conscious observers spontaneously arising from random quantum events. If you wait long enough, 1,010,120 years, a new universe might fluctuate into existence. Eternity is long. Item 95. Digital immortality. Some futurists think we'll upload our minds into computers, achieving digital immortality. Neuroscientist Ken Hayworth is developing methods to preserve brains for future scanning. But here's the philosophical problem. Would the upload be you? Or a copy? If I scan your brain, destroy the original, and upload it into a computer, is that you or a new being with your memories? Philosopher Derek Parfit argued personal identity is an illusion. You're constantly changing anyway. The upload would be a continuation of the pattern that is you. But others think continuity of consciousness matters. If your consciousness isn't transferred continuously, then the upload is a copy, and you died. We don't know. And if we achieve digital immortality, we'll find out the hard way? Item 96. The Doomsday Argument. Philosopher Brandon Carter proposed an unsettling statistical argument. You're a random human. Humans have existed for about 200,000 years. If humanity lasts for millions of years, you're in the first 0.02% of all humans who will ever live. That's unlikely. Statistically, you're more likely to be in the middle of humanity's timeline. So humanity probably won't last millions of years. This suggests we're likely to go extinct relatively soon, maybe in the next few thousand years. This is the doomsday argument, and philosophers have debated it for decades. Some think it's valid. Others think it commits a statistical fallacy, the reference class problem. But it's unsettling. Item 97. Why does anything matter? This is the existential question. In a vast, uncaring universe, why does anything matter? You'll die. The sun will explode. The universe will end in heat death. So why bother? Philosopher Albert Camus called this the absurd, the conflict between human need for meaning and the universe's silence. He argued we should embrace the absurd and create meaning anyway. Psychologist Viktor Frankl survived Nazi concentration camps and argued that meaning is found in choosing how to respond to suffering. We can't control circumstances, but we can choose our attitude. But these are philosophical positions, not answers. Science can't tell you what matters. That's up to you. Item 98. The meaning of consciousness. Why are you conscious? What purpose does subjective experience serve? A philosophical zombie, a being without consciousness, could do everything you do, respond to stimuli, process information, speak. So why does consciousness exist? Philosopher David Chalmers thinks consciousness might be fundamental, like space and time. It's not produced by brains, but rather associated with certain information processing structures. This implies even simple systems might have rudimentary consciousness. But if consciousness is fundamental, it should affect physics. And it doesn't, as far as we know. So maybe consciousness is an epiphenomenon, a byproduct with no causal power. But then, why did evolution select for it? Item 99. Are we asking the right questions? All these mysteries assume our questions make sense. But what if they don't? What if why questions don't have answers? Because the universe doesn't have purposes. Physicist Brian Cox has suggested that some questions might be as meaningless as asking, "What's north of the North Pole?" They're grammatically correct, but don't correspond to reality. Maybe, "Why does anything exist?" is like that. Maybe existence is a brute fact with no deeper explanation. Or maybe we're too cognitively limited to understand the answer. Item 100. You. Here's the final mystery. You. You're a pattern of atoms that became aware of itself. You're stardust contemplating the cosmos. The universe has been here for 13.8 billion years, and against all odds, a configuration of particles emerged that can ask why. You're improbable. If the Big Bang had played out slightly differently, you wouldn't exist. If your parents hadn't met, you wouldn't exist. If a different sperm had won the race, you wouldn't exist. But you do exist. For a brief moment in cosmic time, you're here. And in that moment, you have the capacity to love, create, learn, wonder. You're the universe experiencing itself. So what does it mean? I don't know. Science doesn't know. But maybe that's okay. Maybe the mystery is the point. Here we are. 3.5 hours. 100 mysteries. And you're still here. Let me tell you what I hope you've gained from this. It's not just a list of things we don't know. It's a perspective shift. Most people go through life assuming science has everything figured out. They trust that smart people in labs know how the world works. But the truth is, we're children playing in a vast, strange playground. We figured out some rules: gravity, evolution, thermodynamics. But every answer creates new questions. Every mystery we solve reveals 3 more hiding behind it. Consciousness is an enigma. Quantum mechanics is bizarre. The universe's origin is a puzzle. Life's spark is unknown. Civilizations collapse for unclear reasons. And your own mind, the thing you've lived with your entire life, is largely a mystery. But here's what matters. You're part of the mystery. Every thought you have, every choice you make, every moment of wonder or beauty or connection you experience, that's the universe becoming aware of itself. The ancient Greeks inscribed, "Know thyself," at the Temple of Delphi. That injunction is as important now as it was then, because in trying to understand yourself, you're trying to understand the cosmos. You're not separate from these mysteries. You are the mystery. So where do we go from here? We keep asking questions. We keep searching. We embrace uncertainty rather than pretending we have answers. And we remember that every mystery is an invitation to wonder. If this video changed how you see reality, hit that like button and subscribe. Drop a comment with which mystery shocked you most. And remember, the universe is stranger than you imagine, and you're a part of that strangeness. Thanks for spending this time with me. Keep wondering, keep questioning, and never forget, you're stardust that learned to think, and that's the greatest mystery of all.